Here, and today we're going to be taking a look at how modern Nvidia GPUs do core voltage regulation, because it's quite different from, say, old Nvidia GPUs, AMD GPUs, at least any AMD GPUs that I've measured, Intel CPUs, AMD CPUs, though AMD CPUs are actually getting kind of similar to how modern Nvidia GPUs function, but yes, they're still not the same as what modern Nvidia GPUs do. And when I say modern Nvidia GPUs, I mean like 20 series, 30 series, 40 series. I think 10 series probably also works the same way. I've just not checked, so I'm not sure about that. But yeah, 20 series, 30 series, 40 series use the voltage regulation scheme that we're going to be taking a look at here today. The card that I'm using for this demonstration is an RTX 2080. The oscilloscope is connected to, so the V-core voltage measurement on the oscilloscope, that's the pink one. That's taken with a piece of coax that's just connected to some multi-layer ceramic capacitors directly behind the GPU core, and there's a 50 ohm termination for that at the oscilloscope. And then the V-core current reading is taken with a times 10 probe measuring the output of a Texas Instruments INA 180 current amplifier, which is a little amplifier chip that's designed for amplifying the voltage drop from shunt resistors. It's not currently hooked up to a shunt resistor. It's just hooked up to the power plane of the like the V-core power plane of the GPU. So we're using the resistance of the V-core power plane as a shunt resistor to get a very, very fast V-core current reading. Arguably, it might have some noise issues, and it definitely has accuracy issues, because I have no idea what the resistance of the power plane is. Also, the power plane is made of copper, so the resistance of it goes up and down quite significantly based on operating temperature. So the current reading on the oscilloscope, I have no idea how much current it's actually pulling. There might be, like artifacts in the measurement that aren't actually supposed to be there. We don't really care about that because I mainly have that measurement just to have a rough idea of how much work the GPU is doing. It's not about being precise, because it really isn't. It's fast, it's not accurate. So yeah, and it's like completely uncalibrated because, again, I have no idea what the resistance of the power plane is. It changes with temperature. It's not great. But good enough for just seeing like if the GPU is, working hard or not working hard. Um, so yeah, let's get into it with the first thing that I want to show you, which is mainly just the GPU Z render test, because most of the time, if you run a workload on a GPU, you get an unintelligible mess. But with the 20 series, 30 series, and I think on 40 series you should also be able to do this, but I've not managed it when I last had the 4070 Ti hooked up to the oscilloscope. But I've done this with the 20 series and the 30 series. You can run the GPU Z render test and you get this waveform. And what's really cool about this waveform is that it's not a completely unintelligible mess, because if we zoom in on it, it looks like this. I'm going to try capture a shorter one here. There. And so what we can see here is that right here from the current reading, we can see that we're idle, right? And then this portion over here with a bunch of noise, this is actually load. And the main thing we can sort of, well, okay. So yeah, so this is load, this is idle. You can see that in the core voltage, right, at idle, we don't have really anything happening. It's just a fixed level of voltage right around here. Then when the load starts, we have this big load insertion undershoot right at the start here. And if we actually zoom in on that, you'll notice that there's some like bouncing around, which this seems to actually be a real idle over here. Like I've for a while, I've been wondering if the card is actually dropping to like very low current draw, or if this is some kind of measurement artifact. But based on like multiple captures and sort of preparation for this video, this does actually seem to be a short little idle period, and then it ramps right back up. So we get this like double spike where you have load insertion, load insertion undershoot, then immediate load release overshoot, and then more load insertion undershoot right after. And then we actually have the sort of like, I guess, rendering process of GPU-Z drawing an actual frame, right? Which is the sort of random noise that we get over here. And then at the end of that, we get Oops, went over it. We get this like slight load release overshoot, right? We can see the current draw ramp down, and then it goes up here. And then we have like actually like a little burst of load at the very end. So I guess there's like some finalization process that happens to the frame. Anyway, the main reason I'm showing you this waveform is that center it. Is that it looks very, very similar to something you would actually see in like documentation for real voltage controllers. For example, this datasheet from Monolithic Power Systems from the for the MP2888, which is actually the controller that's used on this RTX 2080 Gaming X. And basically, we're getting a much messier version of what we see right here, right? Where you have that first load insertion undershoot and then load release overshoot at the end of the load. And so that's like the first thing is just, I just think it's kind of neat that there's a real world workload that you can run on some GPUs that produces a waveform that looks kind of similar to what you would actually find in a data sheet, because usually GPUs produce an unintelligible mess. I shall demonstrate. So if we run, say, TimeSpy, we get this, right? Where the GPU is just constantly doing stuff. Also, I'm probably going to have to end the load pretty quickly because the GPU currently doesn't have a whole lot of cooling on it. And anyway, so here you can see that, like, yeah, most of the time the GPU is just doing, I have no idea what, but this is pretty typical of GPUs. They just very, very heavy in terms of like transient loading. Then we have this period of like sustained load where we don't really have a lot of noise, and we can see that that's actually a high level of load because the current reading for that is up here. So, yeah. And so that's like, that's the main thing is just like, yeah, if you run GPU Z on like 20 series, 30 series, 40 series, you get this very like clear idea of what's actually going on to the voltage regulation compared to if you run, well, basically anything else, because if you run anything else, you get something that looks like this mess that we have on on the oscilloscope right now. Anyway, so that's what like the you know, Nvidia GPU underload looks like. And now for the noteworthy thing about sort of this waveform is from this we can actually very clearly see that Nvidia does not use, and technically thanks to the current reading we can also see it from the TimeSpy waveform, but on this waveform it's clearer. We can really see that like Nvidia GPUs don't use DC load line at all. And DC load line is what you would find like on Intel CPUs, AMD CPUs, old Nvidia GPUs, AMD GPUs. And the way DC load line works is this is what you see people call V-droop, right? That's DC load line. The voltage regulator will intentionally lower the output voltage based on the output current. So here in this typical characteristics, like screenshot, I guess, or oscilloscope shot, we can see that we have like idle, right? Because we're going from 0 amps to 150. So this is 0 amps over here. The load ramps up to 150 amps. And the current draw drops off to, I mean, the voltage, the operating voltage drops from 1 volt to like 0.925 here, because we're at 50 millivolts per division. So from here to here is 50 millivolts. We're starting at 1 volt, so it'll be 0.95 by here, and at the bottom of that, it'll be like 0.925, right? And so that's DC load line, and that's V-droop, and you see that on CPUs, AMD, like basically any CPU, AMD GPUs, old NVIDIA cards. And when I say old NVIDIA cards, I mean like 600 series, 400 series, 500 series. Those all use DC load line. Some cards have very little DC load line, but they do still use a DC load line based voltage regulation scheme. 20 series forward, and actually probably 10 series, but again, I haven't checked the 10 series, those use AC load line, where basically the idea behind AC load line is that you do not, like, the VRM ignores the DC component of the current. And in this example, it's kind of hard to see. So, like, you can sort of think of it as like V-droop that only applies to AC current. And in this example, because this is a very clean step load, it's kind of hard to see what's going on with that. But actually, when we get to the oscilloscope, it'll make sense. Or at least I hope it'll make sense. But anyway, here you can see that, we have the same step load, except we have a load line of 0 milliohms, so there's no V-droop. And so we start at like 0 current draw, and the voltage is at 1 volt. Then we have the load ramps up to 150 amps, which creates undershoot, and then the VRM pulls it back up to 1 volt. So we have no V-droop, and we have this undershoot and overshoot instead, because of the load transition, right? And when we transition from 150 amps to 0 amps, we get that overshoot at the end. And that looks very similar to what we have on the oscilloscope. And now, why is it called AC load line instead of anything else? So it's called AC load line because the idea is basically it's V-droop that ignores the DC portion of the current. So if we look at the yellow waveform, I'm actually going to scale it up a bit. Oops. There. You can sort of think of what's going on as, right, like at idle. Also, this is snapping. Oh, it's snapping to this thing. We're going to move that out of the way. Oh, and it's snapping to this label and this window, and it's just snapping to everything. So at idle, we'll have like this level of current draw, right? And then for load, the current draw, you could say the DC current draw ramps up to like this level, right? So like halfway up the noise pattern. And so the VRM ignores that, right? It just completely ignores this gap from here to there. And that's why if you look at the waveform for the actual core voltage, you'll notice that all of the spikes are actually downwards, right? Because the VRM is only adding V-droop to the output when there's a change in current, and it's ignoring the DC portion of the current draw. Because if we had a DC load line on this card, what you would actually expect to happen is that noise pattern that right now is like, oh, zoom in on it. So like we go from idle at here to like your average voltage moves to down around here, right? If we look at it in terms of average voltage, like idle average voltage is up here because there's very little noise. Here the average voltage is a bit lower because there's some noise. And the AC load line is sort of letting the voltage droop and then not pulling it back up super quickly. Whereas if you had a DC load line, you would actually expect the noise pattern to be somewhere in like this area down here. It would actually pull the average voltage down significantly because there's this significant amount of like DC current that the card is pulling. But with AC load line, that just gets completely ignored. And the reason the VRM is designed to ignore or is like set up to ignore the DC current, well, that's just like Nvidia's way of doing voltage regulation. But the reason why it's set up to only react to the AC current is because if it didn't react to it at all, you would have potential like voltage regulation issues, as the VRM would be potentially trying to constantly correct for any minor change in output current, and that can lead to like major voltage regulation issues just because the VRM will be constantly like overreacting to everything that's happening is one way to sort of think of it. And so NVIDIA cards have no DC V-droop and use AC load line regulation instead. And that's just how they work. Now, one of the side effects of this, of course, is your peak-to-peak values are sky high, right? Which, again, we can very easily see in the example waveforms from monolithic power systems. Because if you look at the peak-to-peak for this graph, right, like your peak-to-peak is from here to there. And that is 75 millivolts because we're at 50 millivolts per division, right? So like from here to here, it's like 50 millivolts to down here, that's 75-ish. It might be like 80 or something, but it's a, like 2-digit value. Whereas if we look at the AC load line regulation based scheme, you'll see that, okay, you have this undershoot, which is basically as low as this is, right? It's also around 75 millivolts, which makes sense because if you're like, if the power plane has an impedance of 0.5 milliohms, then yeah, when you go from 0 amps to 150 amps, your current, like the voltage at the load, is going to drop by 75 millivolts just instantly. And the VRM really can't do anything about that. So we get that 75 millivolt undershoot. And then at the end of that, we get the 75 millivolt overshoot for the exact same reason. Like the VRM doesn't see into the future. It can't, react to something that hasn't already happened. So you get the overshoot there. But because of that, the peak to peak on this is from here to here, right? Which is like twice the peak to peak of what you have over here. And so that's why, like modern Nvidia cards, if you ever hook them up to the oscilloscope, their peak to peak readings are sky high. Like on high end GP, like old Nvidia GPUs, high end ones, like say high end 680s, high end 980 Ti's, right? I'm expecting like peak to peak values somewhere between like 100 millivolts and like 250 millivolts. On modern Nvidia cards, you get like north of 200 millivolts peak to peak on a very regular basis. On like the 3060 Ti I had, that was reading up in like the 300 millivolt peak to peak range. And it's because Nvidia has this like really aggressive voltage regulation scheme where it's like, yeah, there's no DCV droop. So any large step in output current causes either massive amounts of undershoot or massive amounts of overshoot, and the VRM will always try to pull the operating voltage back up to the like target voltage, just kind of slowly, right? It's not going to it's not going to try to pull it up super fast because of the AC load line function, which is why, like if we look at the right, because we have that. Oops. OBS is being a bit uncooperative. We have like this idle period right here, right? And if I put the ruler like over it, you can see that, yeah, so the idle period and then all of these spikes are basically down below that because the VRM is drooping for this, like the like AC, like the noise from the GPU. The VRM allows V-droop for that, but it doesn't allow V-droop for the average current draw of the GPU. So yeah, that's how modern NVIDIA cards approach voltage regulation. Now, the obvious question that some of you might have if you've watched a lot of my oscilloscope content might be like, so how does this not crash? Right? Because if you did this, if your voltage regulation looked like this on, say, a static Intel CPU overclock, so let's say you were trying to run like 5 gigahertz at a fixed voltage on an Intel CPU or a Ryzen CPU, and your voltage did this, right here, the CPU would crash. So how come NVIDIA GPUs work, like, at all when they have this insane voltage regulation scheme? And the reason is really simple. NVIDIA GPUs have clock stretching. So basically, anytime the voltage is too low, the GPU temporarily slows down. How this is actually implemented, I don't know. I would assume it's actually a hardware level feature, maybe with some like software level controls over it. But you wouldn't really want to be doing this in software because software can't react as quickly as hardware can. So I'm going to assume it's like there's going to be some circuitry in the GPU core itself that basically manages the clock stretching, and then it either gets like enabled or the degree to which it's enabled is through software. And so that's how NVIDIA GPUs actually sort of like function in terms of power delivery. Is it's just like, yeah, they have no DC V droop at all. There's just no V droop DC. They have ACV droop, which makes sure that the VRM doesn't freak out if there's a lot of fast transients back to back, right? Because you don't want because it's fine if your VRM so the potential issue if you didn't have AC load line functionality is that the VRM would do something like this, and then it would sort of level off. And I did a really bad job of that because that should overshoot. So That's like the usual issue. If you just take a VRM that doesn't have an AC load line function and you just delete the DC load line, you get this. And that's not really a big deal if you only have one transient that you have to worry about, right? Like if you just have one step, right? Like, yeah, so your voltage regulation over here kind of suffers, but it's not really a problem. But if immediately you got some, like if you had a load that looked kind of like this, then the VRM overreacting like this to every single load transition would lead to some major problems, right? Where, okay, so the initial response is like, okay, but then the next transient comes and now it's like, oh, maybe we end up way off where we're supposed to be because at the moment that the VRM is desperately trying to pull the voltage back down to where it's ideally meant to be, the GPU core starts pulling a bunch of current, and now your voltage is falling far faster than the VRM intended for it to. And so that's the idea behind AC load line is basically the VRM doesn't really like it doesn't allow like permanent V droop like you have with DC load line, but it doesn't overreact to every single load in operating current because or every single change in operating current because that would be really bad for voltage regulation if you had a lot of fast transients back to back. Which, as we've seen in 3D Mark Time Spy, is actually very common. So, which is why when you run something like Time Spy or Fire Strike or Superposition, you just end up with an unintelligible mess on the oscilloscope because the GPU load cycles very, very fast. And so having a voltage regulator, like so you can't just have no load line and then it'll be fine. Like no, you also need the AC load line functionality to make sure that the VRM actually maintains like stability in its voltage regulation, even if you have very high peak to peak, so that it doesn't like steadily get more and more out of whack in terms of voltage regulation if you have a lot of fast transients back to back. So anyway, yeah. Also, another sort of interesting thing about this waveform that we get from GPU-Z is you don't get it on older NVIDIA GPUs. I've only seen it on like 20 series, 30 series. I think 10 series would also probably produce it, but I've not checked. But yeah, if you run GPU-Z on like 900 series, 700 series, 500 series, you get an unintelligible mess very similar to what you would get in 3D Mark Firestrike. So, yeah, this is kind of a rare opportunity to have like a GPU produce a waveform that isn't just garbage at a glance. So anyway, yeah, that's everything I really wanted to cover in this video is just modern NVIDIA cards don't have VDroop. Like, at least the usual VDroop that you normally think of with like Intel CPUs or AMD CPUs or AMD GPUs or old NVIDIA cards. But they do have AC load line. So it's like VDroop, but just for alternating current, right? So yeah, and then to deal with the fact that like technically there's still heaps and heaps of undershoot everywhere and overshoot, NVIDIA cards clock stretch to maintain stability. So yeah, anyway, that's it for the video. So hopefully you found this somewhat interesting, if not particularly useful. And yeah, that's it. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And yeah, that's it for the video. So thank you for watching and goodbye.